right, let's go ahead and get started. So thanks for everyone for joining us this afternoon. Today we're going to be talking about taming complex geometries and automating defeaturing of these parts for FEA analysis. My name is Andrew Sutterly. I lead software product management and software partnerships here at Synera. I'm really pleased to be joined by one of our solution engineers, Raid. Raid, I'll introduce yourself.
Yeah. So hi everyone, thanks for joining. My name is Raid. I'm a solution engineer at Synera, so I support our customers automate their workflows, implement use cases during POCs, or also during more advanced implementation phases. And I'm pleased to see a lot of people joining today.
Yeah, a lot of familiar faces with us here today. Nice to see. And as I said, my name is Andrew Sutterly. I lead software product management. I've been in this industry of engineering software now for, I don't know, 12, 13, 14 years. It's hard to keep track. And I really help try to understand what are the problems in the market. And we keep hearing again and again this idea of setting up FEA analyses is tricky, and we're going to dive into that today. But first, I'm going to go in a bit of an overview of kind of what is the problem that Synera tries to tackle at a high level, and then we're going to apply that to the specific use case of FEA defeaturing. So when we take a step back and we think about the way that mechanical engineers like Raid and myself, we've worked in the industry, and we know some of you in the industry work as well. There's a lot of challenges with the way that work is handled today. It tends to be very sequential, whether it's a CAD designer passing a design to a simulation engineer who then passes the analysis results back onto another party. It's this linear steps of work that really creates a very rigid process that creates difficulties in organizations moving quickly. The nature of sequential work also typically leads to silos. So it's not like you have a multidisciplinary team most of the time. Oftentimes it's separate organizations that handle these different disciplines like design, like simulation, like manufacturing, like costing. And it's hard for all those folks to talk together, even if they're in the same building or they're spread out across the world. Collaboration between these silos is not easy. And oftentimes when we talk about engineering software, we're not talking about easy to use applications. We're talking about complex FEA tools. We're talking about advanced CAD tools. We're talking about very specialized costing tools that you really need to be an expert to use. And it's hard to transfer that knowledge and expertise to different applications if you need to switch or onboard other folks into those tools. And of course, maybe one of the biggest challenges we see now in the industry today is all of this is dependent on experience. So, if you have new engineers joining the workforce, they're certainly not performing at the same level that an engineer that's been doing finite element analysis for the past 20 years does. And that obviously leads to bottlenecks in terms of collaboration, but also getting consistent results out of everyone. And so we've thought a lot at Synera about how can we really accelerate these product development processes, right? And if we take a look at what does that standard process look like for a typical design and simulation interaction, right? So you start out with your initial version of a design. You maybe iterate on that with some feedback from your design team, and then your CAD design then goes over to the CAE team, who's working on that initial set of geometry that you provided to them to give you insights on the performance of that part, the durability of that part. And while they're doing that analysis, it's probably going to take them a couple of weeks because they've got a pile pretty high of work on their desk, because maybe there's only 10 simulation engineers to 100 designers or 1,000 designers. And in the meantime, your design team's already iterating on version 3 or maybe even version 4 of the design before they get feedback from the simulation team. And obviously this creates a lot of problems. Either it delays the product development process, or you end up with a design that doesn't meet all of the criteria that you might have for performance, for durability, and these types of things. Could end up in a costly scenario like a recall because your part doesn't meet those desired criteria. And so there's a few different ways that we see people trying to approach some of these problems. The easiest or most straightforward one may be just hire more CAE engineers, hire more people that are experts in HyperMesh and ANSA, and have them, push through that bottleneck of work at a faster pace. But obviously that comes with trade-offs, right? So it's great you get more in-house expertise, but hiring new people, onboarding new people, training them is a very difficult and expensive task. You could start to outsource your CAE. It tends to be cheaper, but you have to oversee those teams that you may outsource this to, or really have a granular look on the quality of the outputs that you're getting there. The most common one I've seen for a lot of my career is the use of CAD embedded CAE. So, you have a CAD tool that a designer is pretty familiar with. You embed some CAE application inside of it, and you start to use that. But the difficulty there is oftentimes getting the designer to really understand the simulation process is a whole other aspect of the journey. It's not just the access to the tool, but it's really understanding of the process. And that leads to lower quality in the simulation results that a designer may achieve. The other side of this, right? So we've talked a lot about manual work. The other side is you can use automation. And I think CAE engineers are great at using automation. I think everyone has their own TCL scripts or VBA scripts or scripts in any different language that connect to their different tools to try to automate those tools and reduce the amount of work that they have to do. The challenge I say there, though, is those automation scripts tend to be only used for a single tool, a single application. It's only useful for Hypermesh, but if you want to switch to ANSA or some other application, then your automation doesn't work there. People are often nowadays adopting Python. I think Python's great. It's free. It's well known. It's got a lot of different libraries and packages available for it, but it lacks the integrations into applications that engineers are using. It lacks the ability to visualize and easily interact with the data that engineers are creating. And so there's inherent challenges with both sides of these. And so Synera, we took a step back and we said, what is the perfect world for an engineer? How can we overcome some of these problems that we see in the engineering space so that engineers can automate any aspect of their development processes in an easy to use way and also easy to transfer way. We want to be able to reuse these automations, whether it's being reused by another colleague or we want to reuse it when we change applications and we start using a different product inside our workflow. And that means this workflow needs to be able to scale with minimal cost. We don't want an automation to be an extremely costly thing. We want to be able to achieve those results at minimal cost. And of course, when we introduce automation, this means that we introduce this aspect of quality that every engineer that uses an automation, whether they're the most experienced engineer or the engineer that's the first day in their job, they can generate results with the same level of quality of that expert that created this automation workflow. And of course, we want engineers to be able to clearly document and communicate their processes so it's transparent for others. I think as engineers, we oftentimes struggle with communication. We often struggle getting our ideas across to other people. And so we want to make a way that engineers have all of these abilities inside one product. And so that's where Synera comes into play. We've created a visual low-code language for engineers that allows them to create their own automations. So automating the manual tasks you may be doing today, whether it's a simple task or a complex task, both are well suited to be automated inside Synera. We have this great process canvas on the left-hand side. And you're going to see with Raid here in a few minutes how that actually works to visually create and document your workflow and share it with others. And then, of course, as I said, we're working with engineering data. We're engineers. We're visual people. We need to see our CAD designs. We need to see our simulation results. And that's where the viewport on the right-hand side really comes into play. Of course, we're not in this alone at Synera. So we operate a marketplace, an ecosystem of connections to third-party software. We're partners with Hexagon, with Siemens, with Autodesk, with Altair, EOS, PTC, and many more to bring connections to all of your favorite engineering products inside this single platform. So today we have over 20 different software partners. We're actually up over 56 add-ins on the marketplace. If you're already a Synera customer or not, be sure to check out our marketplace at synera.io/marketplace to get an understanding of all the integrations we have available today. And I think the biggest thing is the benefits that our customers receive. So we, on average, see a 76% reduction in development time across a wide range of partners, or excuse me, of customers in different industries. But I want to talk today about one specific area. You know, I've been in the FEA space for a while now. I think everyone always has this idea that simulation is easy. We just generate some nice looking plots, and to get from start to finish is, it doesn't take that much skill. But there's a lot of work that goes into FEA, and there's some dirty or not so dirty secrets, I would say. For every FEA engineer, their dream is to get a part like this. It's a simple part. It's a simple assembly. It looks defeatured. It's colored. You can understand all of the different components there. But oftentimes that's not the reality of the designs that we end up working with, right? The reality is maybe you get a design that has all of its fillets already attached to it, or still there. It hasn't been defeatured at all. You've got all of the holes. It's maybe not so easy to apply all of your loads and boundary conditions because surfaces are split. It's not great, but actually the nightmare is maybe more closer to what a lot of people end up dealing with some days. As FEA engineers, your designers just send over everything to you, and you have to figure out how to make sense of all of this. How do I make sense of this complex assembly? How do I get this into a state that I can actually analyze it? Because, the thing that comes out of the design team is not the thing that the simulation team can actually work with readily most times. There's a lot of issues. There's a lot of holes that maybe you need to reduce, a lot of parts that need to be eliminated, a lot of information that's not needed for the simulation process. And so how can Synera help? We have customers like Void Paper that are using Synera today already to automate the pre-processing of CAD designs for their FEA simulations, their CFD simulations, to do things like eliminate the small holes that may exist in geometries when we're talking about sheet metal parts, or to start to defeature specific areas. And they've done this by creating their own custom logic of how to clean up designs in a way that works for their company. So I've talked a lot now. What I'm going to do is I'm going to pass it over to Raid now to dive deeper into the software and show off a bit of how you can actually achieve some of these results with Synera.
Great. Thanks a lot, Andrew. Let me just quickly share my screen and then we can dive into the use cases. Great. So as Andrew mentioned, we'll be talking about how our customers and how you also could defeature geometries and simplify complex geometries in Synera to make them suitable for CAE workflows later on. So as you all know, there's so many facets and aspects to this kind of tasks. We chose 3 tasks to address today. So one of them, I think that a lot of people are familiar with, would be removing small holes from geometries. The second use case I will be showing today is how to remove small features. And as an example, I took imprints. However, this could also be applied to multiple other kinds of features, such as, for example, fillets or other kinds of geometries. And at the end, we will address also mid-surface generation. Andrew mentioned today that Synera is not a closed, it's not a closed software, but it can also connect to third-party add-in. And there we will see also how we can leverage these kind of third-party software to accomplish these tasks by connecting to Hypermesh. So let me start with the first use case. Here I will start with removing small holes. One aspect that Andrew just mentioned is if you build automations, you want the automation that you build to be not very costly. So for this, I chose to build this automation also live in this webinar with you to show how easily this can be done. So what we have at the beginning, we have a part that I'll be showing here that you see to the right of the screen that has a lot of small holes that might be functionally not relevant for doing a simulation. So here we want to build a workflow that imports a part, not specifically this part, but any part. And given a set of rules, it would detect automatically these holes that we can see in the screen. And then it would fill these parts. And after that, we would export it. We could export it, but you could also connect it to a further workflow that you are executing in Synera that also does the simulation directly. So for this, you can imagine the 3 steps of this workflow, or the main 3 components of the workflow, would be importing the geometry, then detecting the holes or detecting the features that we want to remove, and from there on, we move to building the new part, modifying it, and saving it. So let me start with the first step. So here, if I zoom in, you can see I'm importing the geometry as a first step. So by providing the file path to the geometry, which is a step file in this case, I have successfully imported the geometry, and we can see the small features that I just talked about. In this case, we import a step file, but you can have a look also at our marketplace and see the different connectors and translators that we have to different CAD software and third-party software. So this could be also an inventor file, it could be a CAD part, it could be also a SolidWorks or NX, and many other different geometries. And now, after importing the geometry, the first step would be to detect these cylindrical surfaces. So in this case, the feature we want to remove is cylindrical. Now, let me show how easily this can be done in Synera. So the first thing to do would be to take the geometry, and then we look for cylindrical surfaces, and that's what we want to extract. So for now, I didn't provide any further information. All that I provided is I want to extract cylindrical surfaces. And as you can see, it detected all kinds of cylindrical surfaces. However, in this case, as mentioned, I want to extract small holes. So I have a maximum radius in this case, and I know I want to extract closed cylinders. And that's what I will be providing as an information. And then you can see here, we are left with exactly these surfaces in the pattern that we have seen before. Now I'll be connecting this to the rest of the workflow. So the first step to do is, from these surfaces, we want to fill these holes. So that's the goal of the workflow. So now we are left with solid bodies, and then these will be unified or merged together with the original geometry. So now we have a union. And now we can see that just using a couple of nodes, exactly 4 nodes, we were able to detect the cylindrical surfaces and also to fill them. However, you can see here we are still left with some curves that might be non-relevant for the simulation afterwards. So one aspect of this is, since this is a batch surface already, we don't need coincident holes to be on these curves, for example. So therefore, we could also merge body surfaces. So at the end, we are left with a clean body that can be also optimal for CAE tasks for meshing afterwards. And now from there on, if I just move to the next step, I'm just left with geometry that I can export easily. So here, all I need to do is to provide a file path. So now let's call this modified geometry. And then we are left with a successful export. So just to sum it up, to show also how this automation was built easily, in exactly just a couple of nodes, we were able to import a geometry to detect small holes, fill them, and then afterwards, using a union to merge the filled holes with the original geometry, merge all the body surfaces, so that geometry that we are left with is also a geometry that is clean for further tasks for CAE, such as meshing, and then the exported geometry. This is an optional step in case you want to do the meshing in later manual steps. However, if you will be using this geometry in Synera, you will be connecting to the multiple measures that we have from our marketplace. Then you will not be using this step, and you will be connecting directly to the next CAE workflow. So now this was an easier use case. Another use case would be, for example, removing small features such as fillets, or it could be also imprints. Therefore, we have a couple of parts that are a bit more complex than the one that I just showed, where we will be removing imprints. So in this case, you can see the part that we have here. It has these imprints. This could be serial numbers or any other kinds of features. And the goal is using a workflow that is robust, that would work for multiple geometries, not only for this one, at the end, to plug in a file path for a step file and to get the geometry that we see here to the right without any manual steps in between. Therefore, we have this workflow prepared that works with a rule-based approach. So let me start by summing up its steps. So we have a part that will be imported, and then as what we just showed before, we need to find the imprints to detect them. Once they are detected, we need to delete the surfaces. And further on, I will be also showing how from the resulting part, we can directly connect it, for example, to a mesher such as HyperMesh. So let me start with the first step. So here we are importing the part. So I start with providing the file path. And now we can see the file that is imported. The part that is imported has these imprints. So now this workflow works, for example, for products that are aligned in this plane. And what we will do, we will try to detect the imprints by finding the curves that are aligned around these imprints. So if you zoom in here, you see a class of curves that we are interested in. And from there on, using different tools. So Synera is at the end a language or a low-code programming language that where you can build workflows yourself. So you can also come up with your own set of rules. And here we came up with rules that would find curves based on their direction, and then basically these curves would be filtered. So I hope you can see it despite zoom. So if I just tilt it here, you can see these are the curves that actually are exactly at those surfaces that we are interested in. So maybe if I zoom out just to show it so that you can see it a bit clearer, we are interested in these curves here. So these vertical curves, actually, because that's what we can filter to find the surfaces that are imprints in this case. And then after these ones are found, what we do is we use these curves to find all the connected surfaces to them. And by that, we are left by the surfaces that you can see here in blue, and these are the surfaces that would be deleted. So now maybe just for clarity to show it here, so you can see these are all the surfaces that we want to delete. And as of the latest release of Synera, we have a node called delete surfaces. So now all this node needs to take as an input, it would take the original geometry, so the unmodified body. Let me show the inputs here. And then it would take, so this is the modified body without having any changes on it, and then the surfaces that have been automatically detected by the workflow, and using delete surfaces, we would get a modified geometry without any imprints. And here you have also multiple options. So you can define tolerances in case you didn't provide or your workflow wasn't able to find all the surfaces that were provided to the workflow. But you can also define or choose what you want to do with these surfaces. So in this case, we wanted to shrink or grow these surfaces. So at the end, we have one planar surface here, but there you have multiple options. Now, as we mentioned, the goal, if you build an automation, is that you also would be able to use it on different geometries or different products. So now let's see what would happen if we take the workflow that I just presented now and use it on a completely different geometry. So in this case, I will connect a different file path. So for a different geometry. Now you can see this is the geometry that was showed before, and here it has also imprints. And now let's have a look. I didn't do any manual steps in between what the workflow detected. So from this geometry, the first step was to detect curves. And as you can see here in blue, these are the curves that has been detected, and those are exactly the curves surrounding the imprints. And from there on, the workflow creates a bounding box that it uses to automatically detect all the surfaces that are laying within this bounding box, which would correspond to the connected surfaces of the curves or the imprints. And from there on, we can see. So for the sake of time, I'll just deactivate this so that we can directly have a look at the surfaces. And if you look at the resulting geometry, I see we are still seeing the curves that were detected. So I just need to deactivate those or to hide those. And now we are left with this resulting part. So now you can see it automatically detected all the surfaces, deleted them, and we are left with a part that also doesn't have any curves instead of those surfaces. So at the end, we can also provide it directly to the meshing nodes. There, I chose here to connect to HyperMesh. So if we have a look at the meshed part, then it was meshed using one node. We provide the solid body, we just provide an element size, and we end up with a meshed part that doesn't have these small features. And here also we can recycle a lot of results that we generated before. For example, we in order to detect those features, the first thing we had to do was to find their size. So you can imagine you can use the size that we found also here as an element size. So this is one approach, and as I just mentioned, at the end, you come up with your own logic here and build it in Synera. So if you have parts that are slightly different than this, then you can also build another workflow. And to show how this can also be very easily done in case you have processes that are very streamlined, for example, if the imprints have colors already or have any kind of attributes that are coming from this CAD part, then this workflow can be also much sleeker than what I just showed now. So here I will show how this can be done using an attributes-based approach. So what we have is exactly the same geometry. However, in this case, when we imported the geometry, we have the imprints colored in blue. And in this case, we can achieve the same result using exactly two nodes. So each step of the workflow that I mentioned before is, in this case, one node. So we import the geometry. After that, we use filter attributes to filter all the surfaces that follow a certain rule. So here we are using color as an attribute. We provide the color blue, and we are left with these surfaces. And then we provide these surfaces the draw geometry to delete surfaces and end up exactly with the same result.
So Ray, we get a question from Jeffrey here, and I think it's going to be a nice maybe lead into your next example here. He was wondering, we're showing how we can delete geometry inside Synera, but what if we want to interface with another product? What if we want to interface with Space Claim or HyperMesh and interface with their APIs? To do some of these other operations. Is that possible?
Yeah, that is a great question. And as you just mentioned, Andrew, that's exactly leading me to the next thing that we wanted to show. So I mentioned one of the three approaches or three different kind of simplifications that we wanted to address today was mid-surfacing. So maybe just to give one quick answer, Jeffrey, the answer whether it could connect to third-party software would be yes in general, because Synera also, not only Synera has an API, but also we have different tools that we connect to in the marketplace, and we have other capabilities such as scripting, for example. You can include scripts within Synera. You can also use run external program, which means any application that also can run in batch mode that has its own REST API or a COM interface could be connected using these multitude of options that I just mentioned now. And to show that here, I would show how we can connect to HyperMesh. So one thing I showed was how I could make a solid mesh using HyperMesh using one node. That's because we have HyperMesh as a connector or as an add-in. And for that, it's pretty easy, pretty streamlined, and you can just connect directly your data from within Synera. However, if you want, for example, to use the mid-surfacing option or the mid-surfacing feature from HyperMesh, for which we don't have a node, you still can do that using the TCL script, and that's what I will be showing here. So in this case, we are starting with this geometry where you can see it's a solid body, and then the goal is to have a workflow that automatically generates the mid-surface, as you can see here. So also to show this in the viewer first, this is our starting geometry. So as you can see, it's a part that has a thickness, and the goal is to have a workflow that automatically generates the mid-surface here. So if I visualize this, you can see this thin blue line, which is exactly the mid-surface of the part. So how would this workflow look like? As in all the workflows that I showed previously, we always start by importing the geometry. So here we provide a file path, and this is a file to a parasolid file. we import the geometry, and then we provide this file path to a node that would also get the file to the executable hypermesh, to a mid-surface file or target file where we want to save the resulting geometry, and a file name of a TCL file. So this workflow wouldn't only use a TCL script, but it would actually generate a TCL script dynamically. So I can also change the features or change also the options that I'm using. I will go into this node. I will not start showing it in detail, but if you have any questions, if there is any step that you're interested to know, let us know in the Q&As, and I'd gladly also deep dive into one of those points. So here we start by providing a geometry file path, and then the first part would be to import the geometry using the TCL script. So you can see here we have already snippets of the TCL script that are provided, and since Synera doesn't only deal with geometries, but we also have text. We have text modification capabilities. We also have mathematical operations, so multiple kernels. Here you can using these capabilities build your TCL script dynamically. And then from there on, we create a TCL script to replace all the kind of data that we need to change if we get a new file path in the TCL script. And using the run external program node, which you see here, we can run Altair or Hypermesh, so different Altair products using TCL scripts, but in this case, Hypermesh using the run external program in batch mode. So now if I click on run again here, you can see the window that just popped up. And now the TCL script is running for the given geometry. So now I had to click run again. However, what would happen if I just link a new geometry or I just import a new geometry into the workflow? So after we finish this step, I would like to go back to the main workflow and show how this looks like in a complete workflow. Yeah, so now you can see it is successful. So if I go back to the main workflow, then the mid surface has been created. Yeah. And that is actually how this workflow works. I just have to select a geometry from here. Once I selected that geometry, all the steps that come after that, so which is what I just highlighted here, would run automatically. So to showcase that, I'll just click on run again. And then you can see here through the progress bar that the workflow is running.
So just a quick question, right? I saw from somebody here. Is this only applicable for Altair products, or can we do this with other tools as well?
Yeah, so we can do this with other tools as well. I wouldn't ad hoc say we can do this with all the tools that are out there, because at the end, what it depends on is whether those tools allow us to connect with them. So if the tools, as I just mentioned, have interfaces, if it's a COM interface, if it's a REST API, if they can be started using can be started in batch mode, or for example, for multiple software or FEA software such as ANSYS, you have PyANSYS or also PyNastran. You can also use scripts to connect to those. Yeah. So you can have a look at our marketplace. There, as Andrew mentioned, we have multiple connectors. So that's already the tools that you can directly connect using nodes in Synera 2. However, if you check the tools that you are using and they have an interface, then I would say you can also experiment with Synera and try to connect those.
And we got one more question here. How does it handle assembly level features?
Yeah, so yeah, or do you want to? Yeah.
Go ahead, Riley.
Okay, great. So that's also a great question. So here, what I showed parts. So even if the parts are not, one of the parts was complex, but it wasn't an assembly though. However, as I mentioned at the end, you are building logics in Synera. So you can imagine that you can build your workflow also so that it can handle assemblies. We have in the import geometry node, maybe this is a good chance to show that. Or you can activate output assemblies. And if you actually have an assembly, this means Synera will import this assembly. It will still keep the structure of the assembly. So you have it as an information in the workflow. we can deconstruct assemblies. So you can see here, you can access the different levels. You can get also the total transforms, all kinds of information that are included there. And as for example, for the script that I just showed before, you can also run it in a loop in Synera so that you run it for each part of the assembly. And at the end, if you want to do an FEA simulation where you, for example, you define contacts between the different assembly parts, or you are using RBE connectors or string elements between the different parts, then you can also have a workflow that does that automatically. I hope that answers the question.
I think so. Thanks, Reid. And I think we got one last example for us, if I'm not mistaken.
Yeah. So the last example that we have would be an intact example. So here we show how to defeature parts. However, you can imagine sometimes it can get really tricky and messy, especially if you have very complex parts with features of very different scales. And you might be looking also for a solution to actually streamline the whole process. So, and there, Intact comes in place. So it's a meshless technology that you can use, and it's one of our software partners. So we have an add-in that you can directly use from within Synera to connect to Intact products and use their technology to do meshless simulation. And for that, the whole workflow would boil down to a couple of nodes, actually. So here, I will show this on a small part because I think meshless might be also new to multiple people attending the webinar. So here, if I have a part, all I have to do is I can actually define an intact component from it. It will take a geometry. This geometry doesn't have to be defeatured before, since you are using a meshless technology. So you remove actually a lot of pain points from meshing. Then add a material.
Could you just zoom in a little bit? I think it would
Yes.
be good for folks to see the nodes in detail.
Yeah, thanks. I hope this is clear, this case. So here you can see I'm using one node called intact component, and you can see in the inputs it takes a geometry and the material. So that's actually all that you have to provide. So directly after importing the geometry, you can provide it to Intact without having to go through any defeaturing, but also, and most importantly, without having to go through meshing, since this is a meshless method. And then we get a component that we can directly provide to the Intact solver. And then for the Intact solver, you have you can define the different, so the resolution here, which is I think the analogous to a mesh or to an element size in a mesh in a method using meshes. And then from there on, you can also define the element order, the solver type that you will be using. And then we have the result here. So by that, you can remove a lot of pain points, not only for defeaturing, but also for meshing. You can have a look at Intact. You can find it in our marketplace. And if you have any questions there, then I think Andrew or me would be glad to answer those and support you.
Yeah, I think that's one of the nice things, right? I think if you show the solver node a little bit there for Intact, the nice thing here is with this resolution, it allows you to ensure that if you have an assembly with small gaps between parts, typically you run into problems generating bonded contacts between all of these components. The nice thing here is if, with this option of kind of immersing your geometries, your assemblies in this grid structure without having to do a typical surface mesh and then volumetric mesh, you eliminate all of that work of having to join the parts together, eliminate small fillets, all of these types of things. That work goes away when using a solver like Intact. I think we've still got a few questions, but let's jump back to the slides to talk through it. Ray, thank you so much for walking us through these 4 different examples today. I think it was really insightful.
Okay.
All right. And so we just saw a product demo. Now is a chance to do a bit of Q&A. I see we've got still a few questions here, so let's take a look. Bruce was asking, how can you do this on feature or history-based CAD parts? And is the output also a feature or history-based CAD part? Great question, Bruce. So to start a workflow, start a process, I think Raid showed we can import geometry like step files, like NX files, like CATIA files inside Synera and use those and propagate them downstream in a process. The other very nice thing about Synera, we have integrations to all the major CAD products with what we call run CAD add-ins. What this means is actually you can load in your NX file. We're going to read out all of the parameters, and then you're going to be able to update those parameters inside Synera because we're going to call NX in the background for you and update that parametric geometry. So you can imagine in one of Raid's workflows, maybe he goes in and he updates the fillet radius on his part, and it's going to update inside NX, save out the NX file. He's going to have that data preserved for him, and then the whole defeaturing workflow is going to run through itself. So we're able to take that feature-based CAD, use it inside Synera, and then also have that connected to our workflows there. At the end of this process, when you defeature geometry inside Synera, you don't end up with an NX file, a CATIA file, a Creo file. Only those products can, of course, write out native files there. But typically, when we're talking about downstream workflows, you don't need the native file to then go off and run your FEA analysis. All right. Hopefully that answered your question, Bruce. I think next up, we got another question from Jeffrey here. Let's see. So in a multi-tool chain where we're talking thermal results from CFD applied as a boundary condition in FEA, how do we work with those results and transfer them over relevant meshes as boundary conditions in downstream tools? Yeah, so I think here we're starting to talk a lot about, let's say, coupled analyses, right? A coupled thermal mechanical analysis, or maybe one-way or two-way fluid structure FSI analyses. So today we're actually partnered with a few great companies that work on mapping technologies, and we're looking forward to bringing forward some connections with tools from the folks at Fraunhofer Sky with the MPCCI mapper, which would allow you to transfer that information between tools. And we've also got a few other integrations coming soon, not in the space of thermal analysis, but maybe more process simulation mapping, injection molding results onto structural analyses, so you can do a crash analysis. Definitely stay tuned to learn more about what we have in the works there with some of our partners. I see we're a bit over time here, just a little bit. I think we'll call it a day now. So I really appreciate everyone that asked a question, everyone that attended today, and especially my partner in crime here today, Raid, for walking us through a lot of great examples. If you have any questions about Synera, you want to take a look at what's possible, definitely jump on over to synera.io and take a look at our homepage there. And I think also I put our email addresses here, so feel free to reach out to Raid or me if you have any questions, and we're glad to get back to you. Otherwise, thanks a lot again, and have a great rest of your day.
Thanks everyone for joining.